So just again to remind everybody what's happening over here. So what we are trying to understand is the effect within this feedback loop of having these sampling elements within the loop. And so for now, we are still using a continuous process, and in most cases, if we're talking about an industrial application, if we're talking about some kind of situation where we are doing control, almost always the actual thing that we are trying to control exists in meat space. It's not a discrete algorithm. It's not something that we're trying to do calculations on. It is an actual thing. It is an airplane which is trying to dive into the ground. If you've been watching the recent stuff with Boeing, it's quite interesting to see that when controllers go wrong, people can die. But there's an interesting question there about actually, when you think about what that controller is doing, they installed this controller to compensate for the poor flight characteristics that the larger engines in the airplane gave. And so some of you, if you are interested in, like I know people may be interested in kind of fighter jets, and you may be aware that some fighter jets are open loop unstable. In other words, it's impossible to fly them without feedback control. So the dynamics are just so fast that a human pilot wouldn't be able to fly, especially airplanes with large delta wings often are like that. And so this Boeing situation is that the control system is actually compensating and making that airplane easier to fly. But that's just an example of a continuous system. In other words, that airplane, your TC lab, the plant that you'll eventually be working on, all of those things exist in real space, and what that means is that this GP over here, in almost all cases, is going to be well modeled by a set of differential equations. And as I mentioned before, because we are, depending on your choice of terminology, either stingy or fiscally responsible, we want to use the cheapest controller that we can, and the cheapest controller that we can use is a controller that has a very large step size, because the larger the step size, the less computation is required over time. So it means that if I have a machine, a controller, or a computer running a controller every 5 seconds, that machine can run twice as many controllers every 10 seconds, and 4 times as many controllers every 20 seconds, and so on. And so there's a strong motivation to try and use large sampling rates. And I want you to keep that in mind, because I think a lot of people misunderstand the goals of discrete control. I think it's easy to imagine that the pure goal of discrete control is to get a good approximation of the continuous behavior. So many people would say, well, this is a problematic response, these large time steps here. Clearly that is very different from the continuous controller. And our solution to that problem is to use a very small step size. And look, when I use a very small step size, I get exactly the same behavior as a discrete controller, as a continuous controller. And that is not a good way to think, because that is not the goal. Remember, the goal is actually the other way. It's not to try and approximate continuous controllers as well as possible, but to explore the limits of how large I can make the step size and still get acceptable behavior. That's where the interesting part of the analysis is. We've spent a lot of time approximating continuous processes really well by using Euler integration with small step sizes. That's not very interesting. So we are trying in other words, and the reason why we're doing this analysis in the first place and why we're using the Z domain and all of that is so that we can accurately capture the effect of sampling and accommodate it without having to do all of these small step size simulations. So when we left one another, we had, I hopefully had convinced you that, first of all, the discrete step response that we got for just the system by itself, and I'm just going to kind of recap. Remember, we have the kind of journey that we're on is we're trying to do exactly what we did with continuous analysis, where we would say, right, if I wanted to predict that output, calculate that output, what I would need to do is I would need to calculate the Laplace transform of the input. I would need the Laplace transform of all these blocks. I would calculate the closed loop transfer function that relates the input to the output. I would multiply those two together, and then I would invert that transform. And that's how I would go about finding analytically the output at that point if this thing stepped. In the discrete domain, we are repeating all of those same calculations, but we are using the Z transform instead of the Laplace transform. And kind of our first step that we completed yesterday is to say, well, the first thing we need is some way of looking at the discrete response of the hold element and the system together. And highlighting it like this hopefully highlights also the fact that it's not really sensible to talk about the Z transform of GP by itself. And I want to again start waving flags over here. The textbook uses what I believe is quite a confusing notation to refer to the Z transform of transfer functions. The textbook simultaneously uses So what I will call relatively consistently the Z transform of HGP. In Seaborg, they call that thing Z of GP. This is particularly confusing because they will also calculate the Z transform of the input. So in other words, they will say if I have the Z transform of Y, or let's say Y is P of T, I can kind of call that YSP of Z. And so they'll basically say, well, if I have that, and recall that I like writing this hold element in there to distinguish between taking a Z transform which contains only the GP itself and taking a Z transform that takes both the hold element and GP into account. A little bit later this week, you will watch a video of me explaining the difference between the data sheet, which contains a table which takes known functions of time and shows what the equivalent function in Z is. Okay? And in that table, because this thing, you can kind of think of that as being the impulse response of the transfer function. The convenient way of expressing the Z transform of a transfer function, and I want you kind of to resist in your mind thinking about it that way, because technically the Z transform is a thing that exists. It is a property of signals, or it is a property of functions of time. Not so much, it isn't something that we can actually do, it's not an operation that we can actually do on a transfer function. It's an operation that we do on functions of time. So I just want to kind of wave that flag, because this is a large deviation between, if you're trying to work the examples in the textbook, you will see that they use a table for transfer functions that includes the hold element, which allows them to play. It does mean that there's a little bit more symmetry in terms of the the way the transfer functions look, you'll see they never write h. They don't have h in the book when they're working out closed-loop transfer functions. But it's because of this thing. And what that means is that there's a fundamental difference between the table they have and the table that is in the data sheet. It's not a huge difference, it's just that there's a hold element involved in their table, but not in the data sheet. So we've done this, and this is the calculation that we've just completed over here, right? So this is this calculation. This is why I'm doing this calculation, because I'm starting with, I want to know if the controller does things at particular moments in time, what will we measure at particular moments in time after holding those measurements for that amount of time and putting it into GP. And I want you also to kind of remind yourself that that's very different from what I would observe if the hold element weren't there, right? So the math works out differently if the hold element isn't there. In terms of, let's say, reality, remember that these sampled signals do not actually exist kind of as a signal in time. And so it isn't really possible to interface a discrete system like this with a continuous system like that without some kind of hold element. There's no equivalent. Discrete signals aren't pulse signals. Remember, like if you think about something like your TC lab, those discrete signals are literally combinations of bits in the memory of the controller. So there's nowhere in a wire, you couldn't put an oscilloscope there. And it's kind of, a lot of people think this, but it's not true. You can kind of imagine that if this thing, or let's say that sampled version of things, because we use this math, people imagine that, you know, it's these impulses. Now that's the mathematical representation that we use, but those signals do not actually exist ever in an actual wire. You couldn't attach an oscilloscope to a device and see these little spikes, right? So just keep in mind, I've tried to be very clear about that in CPN as well, that this is a mathematical fiction. This idea of this impulse train is not at all how things actually work, right? But it does enable us to do the math easily because the Laplace transform of those impulses behaves the way that we want it to work when we have discrete signals like this. Okay, so in practice, there will always be, in practice, it's kind of a mistake not to have a hold element between a controller like this and a continuous system. So effectively, everywhere where there is a continuous system that wants to interface with a discrete system, there has to be a sampler. Everywhere where there is a discrete system that wants to interface to a continuous system, there has to be a hold element. If one of those cases isn't true, then the system as you've drawn it just won't work. And so we have to figure out what that overall effect is, and that's what we're doing over here. We've got the hold element, we've got G, and in fact what we are trying to figure out is that that combined continuous transfer function over there, what is the associated Z transfer? Now I'm going really slowly in this lecture just because I want you to familiarize yourself with the way that I speak about these things. And I want to have it very clear in your mind the difference between the notation and the way that we talk and the reality of how things actually will be wired together when we build these kinds of things. Because as soon as you start getting confused about those things, a lot of the problems won't make sense to you. So be very careful, maybe rewind this video and kind of watch it again a couple of times and just get a feeling for what I'm saying. I have allowed myself, for convenience here, to slip into this notational convenience of pretending that you can kind of do a Z transform of a Laplace transform directly. But I'll also remind you that technically the Z transform is something that is calculated from time series signals, and so therefore you should interpret this as I'm going to take this transfer function, I'm going to inverse Laplace it to get a function of time. I'm going to sample that signal at moments in time to get an infinite series. I'm then going to do the substitution with the Z. I'm going to find a finite representation of that, and that is what I will call, that is how I arrive at these polynomials in Z minus 1. If that process went a bit too fast, maybe you rewind to your CPN work again, where I kind of said that sentence a couple of thousand times, I think, in class. But the basic idea is that the Z transform is a thing, it isn't a continuous property, it's a property of sampled time signals. But it does help us a little bit to kind of conveniently look up things in tables instead of going through that calculation every time. And we can prove to ourselves that we've done this right, because once we have actually calculated this, remember we are putting in a step and we are observing at the moments in time that we sample, in this case every half second, we're calculating these dots from the Z transform, and I want you to be clear that at this point in time, this plot discrete doesn't actually remember anything about the Laplace transform that was associated with that Z transform. At that point, it's just a polynomial in Z, and we're doing a Taylor series expansion, and we're looking at the coefficients, just like this. So we take that signal, we expand it, and we've got 1 plus 1 cubed plus 1q squared plus 1q3 plus 1q. And those ones, the coefficients of q in each of those positions, is the value of that time signal at those moments in time. And we can see that we've correctly figured out how the sampled signal will work, because when we put a step signal in there, we get the correct output out. More importantly, if we were to put repeated steps into this, in other words, if we would take a step and then do a step at time 2, for instance, we would correctly calculate the combined effect of those multiple steps. Okay, so now we can kind of go through and actually get the closed loop transfer function. That's straightforward enough. A little bit later, I want you also to hear alarm bells ringing whenever you see closed loop transfer functions for discrete systems, because it's quite subtle when they exist. Recall that these kinds of things require that all of the symbols in that transfer function are sampled. And I want you to actually look carefully at the diagram that we've drawn here and understand that we are actually drawing some kind of semi-fictitious thing, or in the diagram here, if the sampler is over there, this is the diagram that corresponds to what we are calculating. In other words, we are sampling what is coming out of the system, and that is what we are calling the output of the system in this particular case. A common different version of that diagram, and kind of, let's say, the common sense version of this is I have my hold element talking to my continuous process. The output from that process is obviously a continuous signal. And I may accentuate the fact that I'm doing a sampled measurement by putting that sampler kind of in that feedback loop position, where I normally would have GM, or like a measurement transfer function, right? And so maybe you could also include some dead time here, but you could have any kind of GM. And remember, that would be a discrete transfer function going back. Now we have our controller. And so in this version, there is no sampled Y coming out of GP. But there is kind of a signal that is the sampled version of that signal. And so if I'm doing the math that I'm doing here, what I would actually be reporting is the sampled value over there. It doesn't make much of a difference to the calculation, but it is very easy to overlook these things when you are just looking at the form of the equations, because it looks so much like the closed loop transfer function that you're used to doing by now just from memory, that you may forget that you're not allowed to take the Z transform of continuous systems in series. Most importantly, if I have a completely different configuration, which is another kind of kind of common configuration which can happen, where I have, I just want to kind of make you aware of this. Let's say I have a continuous process and I have sampled measurement but let's say that that measurement is something like a GC or some slow-moving lab test. So maybe what that represents is a person taking a sample of the actual stuff coming out of our reactor, going to the lab, doing some experiments in a vial, finally maybe like a titration or something, and finally then writing down on a piece of paper what the value of that experiment was, and then handing it back to the people operating the plant, right? In that case, we would have effectively a held measurement. And we could then plug that into a standard continuous controller. Let's say this is a thing that we could do, right? We probably wouldn't if it's like the really bad manual process, but it could be if it's a process that does sampling every 5 seconds or whatever. You know, effectively we've got a sampled signal, and you can see how you could arrive at this place where we had maybe an analog controller and an analog process, and somebody said, well, there's this snazzy new measurement equipment. It's digital. It's much more accurate than the previous one. There's just one snag. It only does a measurement every 5 seconds. So if you just took your analog measurement out and you put this new digital measurement in, that's what you would get. I want you to understand that in this case, there is no discrete transfer function that corresponds to the effect of the set point on the output. So if this is YSP and this is Y, there is no discrete YSP, and therefore it is inappropriate to try to find a discrete transfer function that links YSP to Y. Does that make sense to everyone? And so you couldn't, there is no expression of Y. So you would say something like Y would be just some function of Z. And that function would not be decomposed. You couldn't factor out YSP of Z out of that expression. You could calculate that Z transform, right? Because we know that there is a sampled version of Y over here. So it is reasonable to ask, find an expression in terms of Z that will tell me what the values of that sampled signal is. But that function will change for every different YSP. And you'd have to calculate the Z transform of that whole function instead of going as a transfer function. So with discrete, there isn't always a transfer function the way that we know it, that relates the inputs to the outputs in that nice way where we can factor out the transfer function and the input, right? And it's because of this. So this is one version where we would want to use a discrete transform because we need to take into account that sampling is occurring, but where writing that as a transfer function is not possible. I'm seeing some does everybody understand what I've just said, right? So this block diagram here has a closed loop transfer function. And remember, what is a transfer function? A transfer function is something that has the property that I can write, if that's y of z and that's YSP, I can write a formula of the form yz is equal to something YSP z. Okay? That's what it means for that to have a closed loop. That is what a transfer function is, right? A transfer function is a function of z that can be written in that position, and most importantly is not a function in any way of the input. It sounds very obvious because you've grown used to transfer functions existing, right? I introduced it, and you've used this transfer function idea, so it has become so obvious to you that obviously there will be a transfer function, and the transfer function will only be calculated once. It will be a function of the differential equations that define the system, and I can use that exact same transfer function for all the different inputs. This is not the case for discrete systems when one of the inputs into the system is not sampled, as in this block diagram over here.